Okay. Suppose that the length of an element W from the Weyl group is L. And we have such composition of reflections that gives us such W. And we denote by CK Okay, we have to show that CK and CK plus 1 are adjacent. Are adjacent. With common wall L, B,
guys, maybe we can discuss it.
K.
Okay, so the first part is actually a lot of you did in last homework. In a sense, yes.
What's the first part?
Show that CK and CK plus 1 are adjacent. It was part of the third problem where you need to prove that Weyl group is generated by simple reflections. Well, you can do it like that or in a different way. So some of you did.
I just know that we can explicitly compute the wall that is the common for these two.
Ah, okay. Okay. First of all, we can describe this thing. And we also can say that this thing is lies inside the union of all alpha I, where I 1 to R.
Plus C plus itself. I inside.
No. I mean, not this thing, but it's false. Then we can notice that these things are linearly independent. Hence, we have exactly R walls in this chamber and in all the others as well. We can check it just taking some vectors that are orthogonal just to one alpha I and not orthogonal to the others. So they has to lie in just one of these alpha i's, and then yeah, we cannot cover all the walls by the smaller number of these hyperplanes planes. Okay, then just describe how this ck and ck plus 1 are related to each other using this formula.
So just take inverse of what's written there.
Mm-hmm.
Okay.
And also we can notice that this thing is just S of this composition applied to alpha I plus ik plus 1.
Isn't the second should be like SEK, SE1?
Ah, yeah, okay.
I'm sorry, these ones are dots, right?
What?
Lines. Dots.
Yeah.
Yeah, so you say like it's equal or not?
Yeah, they are equal. Just because we know this fact. Okay, then we just want, okay, and we can notice that this thing is just exactly beta k.
Yes. But if, so you still didn't know that beta k is gives a wall.
Yeah. I just know that we can rewrite it as a reflection with respect to some beta k. Then I have to write explicitly all the walls of ck and ck plus 1 using this fact. Yeah. Okay.
Don't we know if like two wheel chambers can be like one moved to another by some reflection, then the common wall, this root, is their common face, I think.
No, that's not true.
No?
You can move like think of A2. You can move C plus to minus C plus, reflecting with respect to alpha 3. And alpha 3 is neither the wall of C plus or negative C plus. So this is plus, this is minus plus, and this is L alpha 3. This thing. Right? So you reflect.
So we have the following correspondence. And what can we notice? We can notice that if we put here alpha ik plus 1, then these two L's for the indexes k and k plus 1 will be the same. And we also know that these inequalities are preserved by our reflections. So from restriction of this union into the closure of a chamber, we obtain under reflections another closure restricted to this union, to the image of this union. So they have to intersect, and in the intersection will not be an empty intersection with the intersection of the closures of Ck and Pk plus 1. Hence, we have a common wall described as some restriction of L beta k. Okay, now we have to check.
Did we actually use what is written above to conclude that LBK is a common wall? Because I feel like you can just say that, well, if you know how the walls are of a C plus works, like you know they're exactly L alpha K, right?
Yeah.
Then you also know that if you act by some element of a real group on some wall, you'll get a wall of V alpha.
Yeah,
So
we know it.
just from wall you get a wall
Mhm.
because it acts transitively on the chambers and while it's continuous. So
But probably they could lie in different parts of these hyperplanes. So I had to check that this is exactly the same part of it.
yes, but how did you use the first?
I used that they have to give me something non-negative in its image. So we move on just such parts that with this property.
But the fact that it's the same wall follows from just the fact that SIK plus 1 acts trivially on
Yeah, okay.
plus 1. So I don't,
Yeah,
I still
okay.
don't see how
Yeah, since we know this fact, maybe we can immediately say that they have the common wall. Okay, then we have to compare.
I'm sorry, I'm kind of missing. So we know that beta k is the wall of Ck, right? That's kind of clear.
Mhm.
Right? But why it's a common? Why it is also a wall of Ck plus 1?
Because we have the full identity.
I think the crucial part, we just say that, well, every wall of Ck, whatever K we have, is just a combination of S1 as Sk applied to some wall of C plus,
Mm-hmm.
and the wall of C plus is some L alpha, or some positive, some, how to say, simple root alpha.
Mm-hmm. So, may I continue? So we have to compare beta k with beta m. Yeah. Okay. Suppose that this is true. Then we can say that beta k is up to multiplication of -1 is the same as beta m. So just rewrite it by definition, and suppose that k is smaller than m. Then we can rewrite it as so what can we notice? We can notice that if we take a reflection with respect this root, it will be the same as this combination.
Isn't the question of the problem too large? Say that bk not equal to bm. Why we want to prove that lbk not equal to
Yeah,
bk?
this is because this is crucial to the second part of the problem.
Okay.
Maybe not.
So what did I write there?
Right
Yeah,
there.
there was no sign there, but
It should be.
yeah, sure.
Yeah, it should be. So, okay, we obtain the contradiction with minimality of L, because
Yes. Yeah, there's a part of this word that can
yeah.
be shortened.
this length is higher than this one. Okay, it ends the proof of the first part. In the second,
Where you proved everything?
So can you underline the part of word which is reduced of expression? I'm sorry. No, like which. So I think this one is shorter, right? So and this is the part of this.
of W, yes.
And we just take out two elements on the ends. So therefore, this is not reduced since we can make it shorter.
The number of simple reflections has to be the smallest as possible.
Wait a second. Like there, we want to prove that bk not equal to plus minus bm. Okay, that's fine. Then we say that bk bm equal to that. Okay. Then we want to prove that this is not right. Plus minus alpha ik plus 1 not equal to that.
Yes.
Okay.
Yes.
Then we say that s plus minus alpha ik plus 1 equal to z. Okay.
Therefore, we have this. This is some relation on s's.
How we get this? Oh, we just take minus 1 to the left.
Yes, you take. So this is.
No, we don't take anything because when we assume reflections, we don't care about the sign at all.
Mhm.
So this whole point was to just get rid of the sign, I guess, to get to the reflection part.
The whole point is to get a contradiction with this the fact that this expression is reduced. Okay, so we assume. Yeah, sure. We want to prove that. Okay, so we assume the opposite, right? And then we prove that actually some part of this expression can be made shorter. So it's in a contradiction to this being a reduced expression. So therefore, this cannot happen, and we prove this.
Now we have to prove the general formula for the length of an element from Weyl group. Okay, to do it, first of all, I would like to consider the simple reflection as W. And we would like to check that its length is exactly 1. Yeah. I mean that.
So length is 1 by definition, but the right.
Yeah. We would like to check that this
Yeah, the right hand side is 1.
thing has exactly 1 element.
It's actually a definition.
Yeah.
I didn't like
Yeah. Okay, then we can take an arbitrary root alpha and consider a plane spanned by alpha and alpha I. Okay. This is the polarization line.
So what we are trying to do? So there is one obvious root that becomes negative, which is
Yeah.
alpha I. And so you need to take something else and to see that it is.
Yeah, I would like to see that it also lies in R plus. Okay. So we know that psi has to be less than phi. So from this fact, it follows that the reflection with respect to this line of this vector has to lie inside the half plane divided by the polar line.
So why psi is less than phi?
Because we have a minimal angle, so if this thing is less than psi, then we can reflect consider reflection as alpha I, and obtain the next vector which lies closer to this line. So it contradicts with simplicity of alpha I.
But why alpha I is the closest to this line? To the polarization line?
Just because we can construct in otherwise another vector which is closer to this line. Yeah.
So you take. What?
Yeah, why simple root is closest to the polar line?
Okay. We have a finite number of two-dimensional root systems, and we can check it by hands.
Because, well, they have to form a cone, right?
Yeah, we can say so.
So they have to be the closest.
Yeah, okay, and it's obvious then.
Well, it's some kind of an argument that we kind of.
That we believed last time.
Yeah.
Yeah, I suppose last time the second problem was.
Okay.
Okay, not obvious, but we believe in it.
If we imagine at most three-dimensional picture, then everything is okay.
Yeah. How we can imagine more.
All right.
But why are we actually looking into that?
We have to show that all other roots except alpha I will be in R plus after reflection Si.
So we're proving this for L equals 1.
Yeah.
Okay.
If we believe that psi is less than alpha or phi,
For L equals 1 works.
yeah.
And then what?
Then we would like to consider more than one reflection. For example, Si, Sj. To notice that this thing can be rewritten as psi alpha j s I. Yeah. And then notice that after this reflection, pi goes to Si pi. Hence, this reflection is also simple with respect to image.
So you're saying if you apply simple reflection,
Yeah.
then
Simple roots go to simple roots.
It's
not
not
true.
actually true.
No. To simple roots with respect to this reflection. I mean,
Well, what's written on the board there is right, for sure. Because it's just the formula Si Sj, Si Si equals Si
Yeah,
Sj.
I'm what's written next to it, whatever
And
it means.
what's problem? It's not interesting statement. It's triviality, right?
yes.
It's just that positive well chamber, when you reflect, it reflects to the positive well chamber for new,
Yeah.
for image of.
I just consider new
It's like
polarization,
positive
so
chamber is positive.
Yeah.
This kind of stuff.
Okay.
so we have this consideration,
We say it's positive, it's positive.
and then we would like to notice that this product can be written as and we know that these things are checkable with respect to the previous image.
These things are what?
Are simple with respect to the image of the previous part of reflections. This is just the same argument as here.
Okay.
So every time we obtain just one line when we change polarization of a pair of roots. So here we have L lines. Now we have to check that these L lines are different,
Yes.
and this is equivalent to exactly this statement. Just because these lines can be written as R as beta k as beta 0.
Well, to be completely honest, I think the first line that we reflect on is not in that list, right? Because it's not beta k for some k. It's beta 0.
Beta 0, yes.
Beta 0 is not really. Did we?
Yeah, we don't have beta 0.
Can we? I mean, the question is, can k be equal to 0? I think it.
Yes, of course.
Yes, it can.
Yeah,
Here we
equals
just
to zero,
alpha
it's
I.
alpha I.
I1.
Alpha I1.
So there is no need in separately showing it for L beta 0, right?
Yeah.
Yes.
Yeah, here we want to check that it moves exactly one element. And here we split everything into L parts, considered here. So we obtain the number L just because these two hyperplanes are distinct.
Yeah, so I think what you said is actually we already have the C case, right?
Mm-hmm.
And the plane with respect to reflect, the common wall, never changes. So
Mm-hmm.
when you cross a wall, you actually change like your number, this number actually changes plus one or negative or minus one,
Yeah, okay.
right? But it never goes to minus one because wall never, you never repeat the wall.
Mm-hmm.
So that's what we're going on.
So basically, L is just the number of hyperplanes that separate L chamber and C class.
Yeah, I never introduced this, what does it mean separate, but it's kind of fancy.
Separate. Well, it's a rank. I guess it's obvious.
Yeah.
That if you
Just
take any
Technically
point,
speaking, we never introduced that. show that well, like the closure of well chamber is actually fundamental domain in meshing. Oh, we have two of them.
Well, first of all, we have to notice something. So, for example, we have a picture. This is C++. The fundamental domain should be this part without this boundary. So strictly speaking, the closure of C++ is not the fundamental domain. We need to exclude some boundaries.
No, it's actually
No?
We shouldn't.
Why so? We may map the point to.
No.
No, it can't.
This goes to here.
Yeah.
So actually, if you're on this boundary, then your orbit is actually smaller. So your orbit, like if you consider like it's a limit of orbit of bigger orbit where 2 points kind of go to one. Right. Okay.
Okay, then maybe my solution have some problem with these boundaries. So
Okay.
so if we have, for example, 2 points x and y inside the interior, so since the x, y.
Interior should be immediate from what we did, right, in lecture. Okay. So
Yes.
Yes. Okay.
So in the same orbit. Then we can find some number w maps y to x, and we can write the reduced expression I L of w. From problem 1, we see that we can have some wire chambers starting from C++ then to adjacent one and to another adjacent one, but we have the maximum length is a half of the number of r. So this w can never return to C++.
Which number? Okay, L.
L is the length of w. This time.
Right. It cannot be greater than.
Mm-hmm.
So why? So what's the conclusion?
Well,
you would like to prove that x equals to y, right?
well, I want to get a contradiction, so I assume that we have two different points x and y in the same orbit and lie in the.
In C++.
Yes.
Sure.
So.
Then you would like to say that they're equal, or if you assume that they're different, you would like to contradict. Sure.
Yes.
Okay.
Yes. So from problem 1 we can find some wire chamber C++, C1, C2, and 2CL. Each two, Ci and Ci plus 1 are adjacent. So if we look at pictures, it means we have another one adjacent to C++, then another one. But
what is CL?
CL.
Where are you going by adjacent?
Actually, I just want to say it. This is okay minus C++. So from this equality, we can see that CL cannot exceed minus C++.
Exceed doesn't really make too much sense. Right, some number cannot exceed. Right?
Yeah, me you cannot go through here.
So okay, by reduced expression, you cannot go, but by reduced expression you can go anywhere still. So okay, for if my x and y are inside C++,
Yes.
then it's actually obvious, because then this W is such that C++ is WC+. But this just means that length of W is 0. And it's just 1, so therefore x equals y. So that's it.
So
So
W is
there must, the non-trivial part of the problem is for boundaries, actually.
okay.
Yeah. Okay, thank you. Okay, so number 2, you can show us number 2. Yes, that, so you didn't do this? Okay, 55. Okay, please.
So the proof, okay, statement. The closure of this well chamber is a fundamental domain of action of well group. The proof is done in several steps. Firstly, we need to show that each orbit is intersected with our domain, and nextly we will prove that each orbit contains at least one point in this set. So firstly, intersected with this closure only at one point. Let V be some vector since closures of well chambers by the definition cover our space. There is at least one chamber, closure of chamber which contain this vector. Yes. Recall that well group act on well chambers transitive. That's why there exists well automorphism such that we have. So since it is an automorphism, it will preserve closure. That's why we will have that this. So it will send this vector to some vector in this chamber, in this closure. Secondly, we need to check that what we need to check? The following implication. Suppose we have some vector from the closure and
well automorphism such that if we apply this automorphism to this vector, we get to this closure. Yeah. And we need to check that such vectors coincides. It will complete the proof. So suppose we found such pair. Yeah. So we have the following, that the closure of image with its image intersect. Suppose we have non-zero vector, because for zero this part is trivial. Yeah, that's why we will have non-zero intersection by the assumption. That's why this well chamber and this share well. Yeah. So by the because their closures are intersected, it means that they share one face.
No, that's not
C
true.
plus and minus C plus closures of C
Yeah,
plus.
but they intersect only by zero.
But I think in 3 dimensions
In
they
3
can
dimensions, it's
intersect
not true.
by a line.
They can intersect by an intersection of two walls, for example.
Isn't it three-dimensional still by a point?
It so happened that in 2 dimensions the intersection is 0, which is excluded. But in 3 dimensions you might have.
Okay, we will separate in 2 different cases, when vector belong to interior and when it belong to some face. In the if we find such non-zero vector from
Because like from the
You cannot say it's still some statement that might.
from my geometric interpretation, I guess there is no such example.
But root systems are pretty special. You cannot think in generic terms, right? Still, I don't know.
Well, but it's true that the veil group, if it's intersection of 3, and there's the intersection of 3, right? Doesn't really matter.
Okay, so what's going on? So suppose.
Okay, we consider 2 different cases, when vector belong to the to chamber and when it belong to boundary. In the case when it belong to chamber, our assumption implies the following equality: signs automorphism sets connected components to connected components. Yeah, that's why by previous task, it means that the length of this automorphism is 0. That's why it is identity, and this equality is satisfied. Yeah. In the next case, suppose.
Sorry, what's the first case again? We assume that E is in C++.
If it's inside.
If it's inside.
Yeah.
So the case that we have already.
Yes.
Yes, suppose V belong to the boundary are equivalently, it is belong to one of faces. We have in this case we want to check that the length of V must be 1, but so give me a minute.
So it still might not be 1, but the thing is that you have walls, right? Where so it actually belongs to this intersection, right? So how to figure this out? Right. So it belongs to this intersection. Right. But this is some union, some intersection of some L alphas.
Yeah.
So what I claim is that if I act, that W doesn't move this intersection at all.
Yeah, and
why is that? Because you can consider, so you go from C plus, you can consider like an expression, like in the previous problems, like for W, like S beta, what was that, like K, S beta K minus 1, S beta 1, such that these betas are the walls that you cross when you go from C plus to W C plus.
yeah, and
I claim that this is exactly intersection over these betas.
Yeah, and
so, but if you act by W on these hyperplanes, right? So for example, S beta 1 does not change L beta 1. So just it's a stationary subspace.
yeah, and step by step.
Yes, beta 2 it doesn't move L beta 2, but we have their intersections. So therefore, product doesn't change what the intersection of L beta 1 and L beta 2. And so intersection of all these things is not changed by this.
Oh.
So therefore, if I have some element V right from this intersection, then WV is V.
Yeah.
So, yeah.
This completes the proof. Yeah.
You said that you did 3.
If you can use number 1.
Well, I think we can.
Well, you can, if you did it.
Number 1 was claimed, not actually.
Number 1 was claimed, now it's proved.
Not only claimed,
But also used.
Yeah, but
Also proved, but we, on the lecture is not, actually we cannot prove everything. So,
You can't use problem 1 because we discussed it on lecture.
yes, you can.
Okay.
Those would be too much.
it's like something local to the reality function. Oh, wasn't this thing was great that you kind of want to explain what I... Because it wouldn't be great if it wasn't useful, right?
Maybe you come up with some different solutions.
Yeah, but it's hard to come up with a different proof.
Once you
This
know that
thing
it's
is written.
useful.
So it's kind of...
Okay, so we have.
So I just use problem 1. You know, problem 1 that it's such a number of such positive roots that by action they move to the negative roots. Also we use that the element omega 0 is moves every positive root to negative. you also can use problem one and definition such that it's product of simple ones from the lines to see that. And so from this it's obvious such that it is a number of positive roots such that the action of V also takes into positive. Yes. This is equal to 0.
Okay, so this is just problem one. The next equality I was gonna it's alpha in R plus such that
There is still in
we're
R
just
plus.
rewriting this, right?
We're using the definition of or the property of omega 0.
This property, and of course, yes. And this is so then the last equality is R plus minus.
The last is just yes, just definition of length. Oh,
Yeah.
no,
Oh,
not of
okay,
length,
so
but
it's-
of
My solution was right, thank you very much. Okay, 10.4. Right. Okay, Leonid, would you like to?
Okay. But I will not compute all the determinants.
That's so.
Let me make a preparation. If we have two simple roots, alpha and beta, then the possible gram matrices of these two roots are like this. It's obvious. If we have two roots connected with a single edge, then possible gram matrices are the following: 2 lambda, minus lambda, minus lambda. So they are all proportional. If we have a double edge from alpha to beta, then possible gram matrices are the following: 2 lambda, minus lambda, minus lambda, lambda. And finally, the triple edge. So the first vector is alpha, the second is beta. 6 lambda, minus 3 lambda, minus 3 lambda, 2 lambda. And using these 4 basic gram matrices, we will be able to calculate 3 by 3 gram matrices.
I'm sorry, is it really symmetric?
Yes, because we have scalar product, it's symmetric.
It's just, okay.
So if you wish, you can check that these matrices correspond to the definition of these edges in Dynkin diagrams. So our scalar product is positive definite, and hence for any three three simple roots, their gram matrix must be positive definite as well. And so we will consider all the cases of three vectors that contain the following triple root. So it will be alpha, this will be beta,
So what are the cases?
and here we have the third root gamma. Okay, and then we have the first case, this. The first series of cases is when this gamma is connected with alpha and not connected with beta. Now we need to compute the gram matrix. The order is always the same, alpha, beta, gamma. So this here we have alpha and beta, and using that matrix we can write 6 minus 3 minus 3.
And it fix lambda to be equal to 1.
We choose lambda in such way to get this gram matrix. For example, here we have beta and gamma. Oh, not this. Here we have alpha and gamma, alpha and gamma. Here we have 6. Look at that gram matrix for single edge. There we have 2 lambda, so here and here we have 6. So here we have 3, here minus 3 and minus 3.
Wait, what? No, 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 no. I think you have 6.
Okay, yes, 6.
It's a smart way to compute a lot of scalar products.
Yes. And here we have zeros because beta and gamma are orthogonal. And determinant is 0. Six by 2 by 6 minus 3 by 3 by 6.
For this particular case, it's easy.
2 negative 3. I know.
It's one. It's
We
not
believe
three.
you.
It's two.
I'm trying to
It's
find
not easy. It
kernel.
has some square root of 7.
It's 2 to
In
1.
the
It's 2 to 1.
no.
That is
2, 3, 1.
2 to 1. If you multiply the
Ah.
2, 6, 2. 6,
Yeah,
3,
okay.
3.
No, we're finding
Three.
something in the kernel. That's what.
Okay. But
Okay,
it is just an exception. All the others, almost all the determinants will be non-zero, but negative.
Well, there are 2 cases in which
I suppose one is beta.
Okay,
but
2 k.
also 2 is
well, if you put gamma to be beta, you also should.
Yeah, yeah, with one edge.
At least I got 0.
Yeah.
Maybe I'm
Me
wrong.
too.
Okay.
But it's not beyond me.
Well, let's
I said
continue.
almost.
Let's continue.
Okay. We have 10 more cases.
It's good when you mistake into negative values.
Okay. Honestly, I computed 6 of the determinants by hands.
Maybe
Okay. Let's do it.
So 11, so you have also cycles, right?
Yes, I can
And
just.
also
Yeah, but there's
Okay, if we understand how to write these gram matrices, then we can skip this part and I'll just write
Yeah,
the
kind of clear,
cases.
yeah, can you just write at least determinants?
At least determinants without matrices.
Yeah. I was
Did you solve this problem?
no.
Okay, you just want to look at the numbers.
I
I can just read it. Minus 36, minus 9, minus
There's
108,
always will be minus or 0, yeah?
minus, and in 2 cases it will be 0.
So there's no any interesting cases.
In some at some point of view, they are all
No,
interesting.
I think you have to at least write what are the cases.
Okay.
There are also cycles, right?
Yeah, can you just draw
Okay.
all the cases so that
Yeah, I just wanted to see examples because I didn't write it and I didn't know that that's all negative numbers. So I just
They were positive and it would be hard to
yeah
reduce systems do not exist.
yeah. So that's
Actually, I don't know if there is like any other way to prove that something is non-existent other than proving that this form.
you can kind of so it's not that dumb when I thought about this. So like in Humphreys, you prove that. So remember, we proved that you cannot have valency 4, and this actually is applied even. This the same kind of proof is applied to all these cases. So actually, this can come like from one edge, like vertex. This is from another. This is still prohibited. So such situations is like the 4 valency for this one. So that was an idea.
That's hard.
you have 8 and 9 are equal.
Oh yes, they are.
7 and 9 are equal.
Okay.
Well, you always have to solve
Yes.
things.
I need something like. So with double three edges, we have this, and 2 edges looking to the same vertex, to the one vertex. Yes. And 2 cycles. And we don't have other cycles because of lengths of roots.
Can you explain this a little bit more?
Okay. So assume this length of this root is x. Okay, square of length. Then square of length of this root is x divided by 3.
Yeah.
And this is also x divided by 3, and they must be equal. So there is no such cycle, because this is x divided by 3, this is x divided by 6. And this is x divided by 3, must be.
Okay, thanks.
So that's all.
Okay.
And for each of these cases, we need to write the gram matrix and compute its determinant and check that it is negative or 0.
Yeah. So in this case, thank you. You can write a Cartan matrix, and Cartan matrix is like that, like 3 vertices, and then negative 1, negative 3, I think, negative 1, and negative 3.
I see. Okay.
So maybe somebody can easily show this. I don't know. Mark, maybe you can show. Okay.
So like first part, it's just like we have some useful system, and if two vertices have connection by one edge, then we can just restrict it to that and construct some, and we just get a reducible reduced system for R2. And this type should be A2. Because obviously it's not some exceptional, some exceptionals, but B2, C2 should have, B2 and C2 looks like with two vertices, and D2 should, well,
D2 is just
it's
not
like that.
yeah, it's not irreducible.
Yeah, that's why it's only A2, and for A2 we know that like this A, this B, and this C forms this alpha plus B.
Mm-hmm.
And we just know that we can compute beta by symmetry like that. Well, it's probably just, you can look on a picture and it's just like that. And probably you can also compute it by some coordinates. But yeah, it's just like that. So that's the first part. And the second part, it's transitively on the set of all roots of the same length. So for AN,
So we're not checking it for B and C.
what? This one?
I think this is the same as beta as alpha.
This.
Well, it has to do something with beta alpha stuff.
Well, why we should, it's
Because
given
everything is simple. It's given by simple introductions over size 2 because
yeah,
you want to.
you asked earlier the question that
Yeah.
for beta and C,
Yeah,
why
well,
we should. That's the question, like
because
connected
we
by a
don't
single
have,
edge.
yeah, we don't have some.
Yes, so that's not how.
Well, these points are also simple roots in our sub-system. And we know
There's no
we can-
statement in that cases.
And we know actually that this edge is the same as gives us like some particular angle between that.
Why do we actually consider only two-dimensional?
Well, we restrict to this.
It's a statement about two vertices
Yes.
so far.
If you have two vertices and then it will be something here, something bigger, we just want to restrict and this will be reduced to a system. So that's not nothing to think about, I think. So yeah, for AN and TN, it's easy because they're connected.
Is it true that if you have some graph and you take some subgraph of it, then you will always get a reduced root system?
For two, it's true because
No, for 2, yeah, but just in general.
no, because you can just
No.
take something like this. So just two vertices. No, I meant something like two vertices. Just
Okay,
this subgraph. Well, if you take connected subgraph, then it will be a reducible root system.
But what's wrong with this one?
It's not connected.
So what?
I
Well,
take
we
this.
just take 1 and 1.
But it's still You think it is should be irreducible? Okay.
Yeah,
Yeah. Okay.
suppose we're talking about Lincoln diagrams and
Uh-huh.
irreducible
Uh-huh.
reduced sources. So yeah, I want to finish the proof.
Mhm.
A and N is connected, and all of simple roots has the same length, and it's acts transitively by the first one.
Mhm.
Just okay.
So in your Dinkin diagrams, you just should erase the multiple edges and see how many connected components there are.
Yeah.
And in all of them, you would have, wait.
Well, 1 minute. So
That what I'm
for
saying.
B and C, and we have all of but one have the same length, and
Yes.
it's connected. Then they have transitively
Mhm.
have well group action of well group is transitive on this
Mhm.
sub-reducible reduced root system, and on the last one,
It's transitive on simple roots.
yes.
Oh, and then we are simple roots and then
Yes, but in the problem we need to prove that it is transitive on all the roots of the same length.
Well, actually, it's true. I see it
oh,
already
I
now.
think maybe all simple roots of the same.
Yeah,
No,
it's
because of transitivity, this Savian to check for simple roots.
why so?
Because
Because
all
if
other
simple
roots are generated by action of
one
while
orbit,
group.
then all roots which are
If they have same length and they have some.
All other roots are obtained from simple by action of while group.
Yeah, but what if
So of course,
something strange? What if like what if two roots have like it's have representation of by simple roots, and what if there is roots with
and so suppose that you have a root, so of some length, then it's obtained by action of while group from some simple root of this length.
Is it obvious?
is it obvious?
Well, while group is reflections. Reflections doesn't change length.
It doesn't change length.
Is
Yeah.
it obvious that it follows from the fact?
That
Yeah.
R is WP pi.
From this fact, it's obvious.
Yeah.
Yeah. Okay. Then it's just wanted to prove for simple. Okay. Yeah. And then there only one root of not the same length, and it's everything acts transitively on the set of one element. So yeah, for E6, E7, A and E8, it's still connected, and they all have same length, so it's by one. For G2, there's two roots with the
Different length.
length, so it's acts transitively, obviously. For F4, we have something like that. Yeah, and these two have same length, these two have same length, and others two doesn't have same length. So you like this and this doesn't have same length, and each pair doesn't have same length, but this. So and this acts transitively by one. That's all.
Yeah. What else? I think we. Yeah, I think that's it.
This all is actually.
Yeah, it would be not true, right, if we have some Dinkin
Well, if you have some
diagram,
like
like maybe this, right? That would be better.
yeah,
Like this and
that's
then like
yeah.
this.
Mhm.
Then this of the same length, but they're not. Okay. Right, so that's it. The 7. Ну, я по большей части слышал приватные. Извращенный это как-то... Ну, если бы он писал русскую статью, он бы это использовал, я не знаю. Не дадут этого финансирования там, что типа, чем вы вообще чем занимаетесь? В отчет никак не. Извращенные пучки. Да.
Мы могли хуже пойти.
Так. Let's start then. Right, so maybe today will be, so I hope the last lecture on structure theory, and next time we will start representation theory. So, which is of course related, but still. So consider the following decomposition of my semi-simple algebra like this: n minus plus h plus n plus, where h is Cartan subalgebra and n minus or plus are this. These are G alphas such that alpha is either positive or for minus it's negative. So such thing is called triangular decomposition. So again, let us have the same notations that we have. So R is now the root system corresponding to a semi-simple algebra G, and then you have simple roots, R of them where R is dimension of H. So actually let me choose, so for each I, let me choose an element EI in G alpha I and Fi in G negative alpha I. Then we have the following proposition. So first of all, regardless of this choice, actually, n plus and n minus are Lie subalgebras in G. Of G. And second, which is less trivial, is that n plus is generated. I'm sorry, so. The freedom, yeah, that doesn't really matter. Just some rescaling. Yeah, we will need to fix it at some point today, but so far we don't need it. Of course, I don't want them to be zero, right? The only thing. Right, so n plus is generated by EIs, so E1 and so on, ER. And similarly, n minus is generated by f's, f1, fr. So let's prove it. Proof. First one is very easy to observe. First follows from the following, that G alpha commutant with G beta is G alpha plus beta. That's it. Then number 2 is a bit less trivial. So here we'll need some observations about root systems. So let me choose some alpha which is positive root, but not simple. Then I claim, I claim that there exists some simple root such that its inner product, or whatever, killing form, or like induced by killing form. So inner product that we have there is greater than 0. Indeed, suppose the opposite. So if for every I from 1 to R, we have this, then we have that the following set, alpha, alpha 1, and so on, alpha R, is linearly independent. So the proof is the same as the proof that simple roots are linearly independent. Right? We started with this condition that alpha I, alpha j gives me not positive inner product, and then we proved that they're linearly independent. So here the situation is the same. So if I suppose that they all give this, then this set is linearly independent, which is, of course, contradiction, because alpha 1, alpha R give me basis. So proof similar to the proof of linear independence of pi, but this is contradiction to the linear pi being a basis. In where? H, R, star, right? This statement is actually not about semi-simple algebras, but about root systems. Okay, so suppose that I found such alpha I, that alpha I is greater than 0. Then I'm going to use it. So then, of course, alpha with negative alpha I is less than 0. But this means that sum of these two is a root. Alpha minus alpha I, which I will call beta, is a root. This can be, this is again statement about rank 2 root systems that can be checked. But also I think we used it in some of the problems when we proved that alpha 1 plus alpha 2 and then so on until alpha r is a root. Yes, okay. Yeah, but this is check for rank 2 root systems. Then what? So since this is a root, I know that G beta with EJ is G alpha then, right? Because this lives in alpha I, and beta plus alpha I is alpha. Very well. But then I also need, so you see the logic here, right? So I take some root alpha. So what I would like to prove, I would like to prove that, where is my proposition? That n plus and n minus are generated by these things, right? So I take actually positive alpha, right? Consider G alpha, like an subspace in n plus, right? And then I say that it's actually generated by action of G from some other root, beta. I also would like to prove that beta is positive. So claim.
Yeah, the generated mean if you close it by commutator and.
No, this one is one-dimensional.
Yeah.
So it's just like that.
No, I mean generation.
Oh yes. Generated as a Lie algebra. Yes. The only operation that we can use to generate something is Lie bracket. Okay, so claim beta is positive. All right, so this the second part, yes. So beta is positive because if I write alpha as a sum of some coefficients non-negative, so like this. Right, then beta is then sum over nj's, alpha j's, where j is not I, plus ni minus 1 alpha I. So all right, then I would like to say what? If ni minus 1 is non-negative, then I'm done. So if ni minus 1 is greater or equal than 0, then beta is from R plus. But if otherwise, we have a problem because, so if ni minus 1 is negative, right? This is decomposition of a root in simple roots. This one is negative, but we have either positive roots or negative roots, nothing in between. Right, so either all coefficients should be positive, or either all coefficients should be non-negative, or all coefficients are not positive. Okay. So if my root is positive, then all coefficients are non-negative. If it's negative, then it's negative for a positive root, right? Then the opposite.
Well, it's some. So why? simple roots. But why if beta can be written by
Something else?
Yes.
Because this is a basis. Yeah, there's no other. So if it's negative, then the only thing that I can have is that nj is all nj's are 0. Right? Because beta is either
We'll still have non-negative.
yeah, either beta is either in R plus or in R minus. So that's how I would like to write about our discussion. But this also means that ni is 0. Right? The only way to do this is actually that is ni is 0, so therefore alpha is 0, right? Which is, of course, contradiction. Alpha is a root. Contradiction. Because ni is some non-negative number, integer. So if it's 1, then it's 0.
why it should be integer?
Well, because
Something like 1 half.
because positive root is a sum of alpha i's with positive integer coefficients. Yes. So we proved that beta is in R plus. The only thing that I need to do to finish the proof is to do some induction, right? For induction, I need to introduce height. So denote height of alpha to be sum over I from 1 to R of these numbers and I. Then part 2 follows from this. I don't want to reach g beta with e j whatever. Imagine a star there. Okay, so maybe, all right. Just to. So this is star. By induction on height of alpha. Well, n plus is this part. N plus is generated by EIs, but of course the n minus is similar. Okay, so now comes an important part, which is hard part, so we don't have complete proofs. So Serre relations. So now let me fix theorem. This one is not hard. This one we will prove. So let me fix now the lengths of EI and FI. So for each I from 1 to R, let EI from G alpha I and FI from G negative alpha I be such that the inner product is what we already saw sometimes in the past. It's like this: 2 over the square of the length of alpha. Okay, so then E, I, F, I from 1 to R, satisfy what's called the Serre relations. So what are those? So first of all, EI and FJ commute for all I not equal to j. Then secondly, I didn't introduce one important thing. Where would I like to introduce it? So maybe here. Well, we already saw that, but okay, let me introduce it officially. Definition, Cartan matrix is the matrix A with ijth entry. So maybe is n R by R matrix with ijth entry, aij equals to n, but I will need alpha j first, some technical reason. So like that, this is my definition of Cartan matrix. So
it's like transpose?
Yeah, that's the definition. So we kind of never did it in detail. I think in one of homeworks I introduced, but that's not that was transposed. Yes. So this is what I need.
Yes.
All right.
So usually it's like that, or it doesn't?
You know what? I always work with GLN, so. So I honestly I don't know, but in Kirillov he actually yeah. Yeah. So this is our convention. So maybe I don't claim that everywhere we have such a convention, but all right. Then another relations are if I apply at EI how many times 1 minus aij of EJ, right? This equals to 0. Number 3 is that at Fi 1 minus aij to Fj is 0. Okay. Sometimes people include some obvious relations that we have from the root decomposition and call them Serre relations. But I'm more used to calling rather this two to be Serre relations. Okay, this one is also not so trivial, so include it in here.
Is this for I not equal to j?
Yes, yes, sorry. So all this is for I not equal to j.
Okay. Aij in this case are negative, right?
Right.
Okay.
Okay, this one we can prove. Proof. Okay, first let me prove the number 1. And notice that EI Fj is inside G alpha I minus alpha j. But alpha I minus alpha j is not a root. For the same reason as we that we used here, the same argument, right? If I have a root, then its decomposition into simples have either non-negative coefficients or non-positive. So this cannot be a root. Sorry, like this. So therefore, this is 0, and we have 1. EI Fj equals to 0.
How did we get that commutator of EI and Fj is in there?
So this thing, if it's a root, then it's not 0. If it's not a root, then it's 0.
That we had long ago, yes?
But this is just by definition. This is just by definition of roots. So root is a common eigenvalue for H.
Well, I suppose it's just because commutator of G alpha and G beta is equal
So
to
what is our definitions of root system for semi-simple G? We had this root decomposition where this is set, right, such that G alpha is not 0. Maybe. So by definition, if alpha is a root, then G alpha is not 0. If it is not a root, converse of that, then G alpha is 0.
I was just asking did we get that, the
This one.
This is something we discussed.
This is because G alpha, G beta is actually equals, right, to G. This equals only if, so inside I should write. So equals if this is a root.
Yeah, it's fine.
Why alpha I minus alpha j is not a
There's one negative.
Yeah, why is the same?
It's neither meat nor fish. So it is not negative, not positive, right? It has positive coefficient and negative coefficient. This does not happen. Should be either in R plus or in R minus. Seems like I'm tricking you, but actually I'm not. So, right, you have this. Let's prove number 2 then. So for number 2, we would like to recall this V, this irreducible, what was that? Irreducible representation of some SL2 triple. All right, so that was sum. So this is a comma here, right? Sum over k from z, and I have g negative alpha j plus k alpha I. And this is irreducible representation of SL2 corresponding to the root alpha I. That we proved last time, not last time, but maybe some number of lectures ago. All right. So now I look at here. So this is 2 stars. So from 2 stars, we know that Fj, and Fj, by the way, is inside this V alpha, negative alpha j alpha I, right? With k corresponding to 0, is a highest weight vector, is a singular vector or whatever, singular vector. And highest weight vector of which weight? So if you go back, we actually computed this weight, and it was like this. The weight corresponding weight lambda was n negative alpha j alpha I, which is negative 2 alpha j alpha I over alpha I alpha I. So it's the highest weight vector of this weight. Therefore, we have, if we act by fi sufficient number of times, we will get 0. Right? It's just how a representation theory of SL2 goes. So it means that if I take fj and apply at fi how many times? Lambda plus 1 times, I will get 0. Because, well, you remember that if I have highest weight vector lambda, I go with the step 2 until I reach negative lambda. And then if I try apply f one more time, I will get 0. So that's exactly what's written here. And this is, by the way, negative a ij. Just by definition. Capital, right? We had capital A. We had the capital and small. Small here, capital. So that's capital is not very good to write in the superscript. So let's go to small. So we proved number 3. Number 2, it's just the same reasoning. You just need to consider lower weight vectors. You know, a little bit reverse picture of that. So yes, I think it's the same. Alpha I minus alpha. Yes, yes. And j should be like a lowest weight vector. And so it goes from the low to highest, and then you apply E one more time, you get 0. All right. So we proved that cell relations hold in G. And then, so usually these generators, EI, FI, and HI are called the Chevalier. It's EI commutator with FI. Yes, it's H alpha I generators. All right. Okay, and here comes difficult theorem. But it is important, but the proof is pretty technical. And I mean, we need maybe another lecture or maybe more to prove it. So we'll not, I don't know, maybe it's fun, but let's just move forward. So, but theorem is important. We state, we claim it, and we will use it in homework, maybe. I don't know. The theorem is like that. Let R be a reduced would I like to add a reducible? Okay, just reduced root abstract root system. And pi well, you fix polarization fix. This gives you some set of simple roots. And let GR be the Lie algebra with generators. Well, some generators E I tilde, F I tilde, H I tilde, where I goes from 1 to R, so this R. And generators and relations. So all relations that I impose, I like this. So HI with HJ tilde commutator is 0. Then HI tilde EJ tilde Lie bracket is AIJ E, so this is J, EJ tilde, and HI FJ is negative AIJ FJ. So this is this, of course, AIJ, also I should say, right, A, which is AIJ, is the Cartan matrix. So I have these three and, well, Serre relations. So just change this to tildes. So let be GR be like it's written here, right? So I am actually taking free Lie algebra, right, with no relations, and quotient it by ideal, which is generated by these elements, right? So this minus this minus this, and corresponding. So this is what it means, like with generators and relations, right? We never discussed it, but it's clear what it means, right?
Yeah, and free Lie algebra is commutative?
No. It's it's like furthest from being commutative.
Yeah, so like if it generates by something like alpha beta, what is commutator of alpha beta?
It's you just add this element as a basis.
So in some way, just the vector space of all possible commutators.
Yes. Okay, so the statement is that then this algebra is semi-simple.
Is it actually obvious that this is a Lie algebra?
Yeah, you need also, well, so you need better understanding what is free Lie algebra, because you need what?
I think you know that it is left and right.
I don't know, I mean,
You need Jacobi density, right? Once you understand what is free Lie algebra, then sure it is a Lie algebra. Or you still can get like algebras by generators, Lie algebras by generators and relations.
well, my issue is that, like, well, okay, you have some relations, and you assume some ideal, right? Generated by all this.
Yes, yes. So if I already have Lie algebra, I can quotient it by an ideal and get another Lie algebra.
Yeah, well, okay.
Yes. So then GR is a semi-simple Lie algebra with a root system R. For us, it means that it has some Cartan subalgebra such that corresponding root system is R. But maybe we will cover this unfinished business today as well, about existence and uniqueness. So this is the statement. So corollary, okay, we will not prove it, but still it's an important statement to know.
Written somewhere?
Yes, in Humphreys, for example, in Serre. So I was trying to maybe squeeze it in, and but I mean it's a lot of steps, and actually he develops a lot of results before like that we like you still need to work this out. Yeah. I think the most non-trivial steps to prove actually that it's finite dimensional in. Yeah. And we don't claim uniqueness yet. So today I would like to do this unfinished business with existence and conjugacy of Cartan algebras, and then this will mean uniqueness. Okay. So corollary that we have so far is that if I have G with some root system, so if G is semi-simple with root system R, then G is isomorphic to G of R. So you can go backwards at least. So this is true because well we have so maybe proof, I don't know. If you take tilde generators here and map it to EIs, and of course Fi go to Fi, Hi goes to Hi. So first of all, this is This is a homomorphism of Lie algebras.
I think you need to tilde going some. Like, is it homomorphism from G to GR?
From GR to G. Yeah, I'm saying isomorphism, but it's actually, for me, it's better to do it this way, because I proved that in G I have cell relations, so therefore this is homomorphism of Lie algebras. Okay, but also it is surjective. It's surjective homomorphism, right? Because these are generators of G. Okay, you have a question?
Yeah, this corollary seems to be just the opposite statement, no? Like, in a way.
No. It's just.
Well, what is G then? Like.
So suppose you have semi-simple Lie algebra G, and suppose you found a Cartan subalgebra such that the corresponding root system is R. Then the statement is this algebra GR is isomorphic to the semi-simple Lie algebra that you started with. So this is why you make a homomorphism like that. This is homomorphism because we proved that in G we have cell relations, and we proved that, and it is also surjective. So by propositions or whatever, by propositions, by what is proved before, this phi is surjective homomorphism from G to from GR to G.
Isn't it statement that what we constructed theorem is unique?
No, not yet.
Yeah, but why? Like we have R, we construct G of R.
What?
So when we again construct by this R some other G of R, this should be isomorphic to it. Just
So suppose you have two different.
so if you have G of R and G tilde of R, yeah, and G tilde of R is constructed from R.
Yes.
So G of R.
So uniqueness of what you would like to do?
Uniqueness of G of R. What uniqueness?
This is unique by construct. You just give. So unique.
What unique we want to? What uniqueness we want?
If I give you two, so there are no two non-isomorphic Lie algebras with one with the same root system. That's the uniqueness I would like. So this map actually is, we have a map from R, from root systems to semi-simple Lie algebras. So far I cannot say if it's even surjective.
Yeah,
So
but if it has the same root system, then G1 is isomorphic to G of 1 of R, to G of R, and
No.
G of R is isomorphic to G of 2, isn't it?
So suppose that I have G1 of R.
No, you have G1 with R.
Yes, G1, yes, so I have one root system. And G1, G2 corresponding to this root system.
Yeah, so you construct G of R, and it's isomorphic to both of them.
Yes, I construct G of R. Then you're saying that
No, you're constructing G1 of R and G2 of R.
No,
but how? No, there's only one G of R.
G of R isn't.
Okay, yeah,
That's the
Yes.
polynomial of R.
So then G1 of R is isomorphic
What is
to
G1
G
of
of
R?
R, and is isomorphic. Sorry, G like this, right? G2.
Yes, so by stratification of isomorphism.
Yeah. Seems to be.
Yes. Okay. Yes. Uniqueness is there, but surjectivity is not there yet. Okay. But let us finish. So this is surjective homomorphism, but we actually can compute the dimensions of G.
Why against subjectivity?
Yeah, yeah.
Surjectivity because these are generators in G.
Okay.
So we actually can compute that dimension of G and dimension of G of R are the same, and they equal to what? Pi plus what? Pi plus R. Pi plus R. So you have roots, and you have Cartan subalgebra. So these are all roots, this is Cartan subal. So like this.
Yep.
So therefore isomorphism.
You said like that this theorem with this corollary doesn't give us subjectivity?
Yes, because maybe we didn't prove that we have Cartan subalgebras.
Ah, okay. Yeah, that's
So let's now do this unfinished business.
yeah, that's true.
So unfinished business. But I will do this. I will try to do this all at once to prove that.
So isn't dimension should be just cardinality of R? So why is it P plus cardinality of R?
So you have Cartan subalgebra of dimension p of dimension pi, like size of pi. Plus you have roots. Actually, yes, yes.
So how do we know the dimension of G of R is exactly this?
Because it is a semi-simple algebra with root system R. Both G and G of R. So that's why it is a corollary of the theorem. So it is, yeah. All right, so I will try to prove all at once that still we have uniqueness, but we don't know that Cartan subalgebras are conjugate to each other. So what does it mean, first of all? Yes, so what does it mean? So by definition, I say that two subalgebras say H1, H2 are conjugate if there exists some element G, it is from group G, right? So this one is a connected Lie group such that its Lie algebra is G. If there exists some element of a group such that add, like big add, G of H1 is H2. So there is some automorphism of the Lie algebra, and actually, like in the this size automorphism. Okay, so then I don't know, theorem.
So this is the differential
Of well, it is a joint action of a group on its Lie algebra.
but like, how is it defined? Is it differential of something?
Differential of conjugation. Yeah. So theorem is the following. So Cartan subalgebras. No, you can take, yeah.
So it's like if some
No, you just need, so if you found some element like this in one Lie group, the question is if you can find in another.
Well, I suppose you can do something like you can take connected, semi-connected, simple connected Lie group, and then it's have like.
Is it true that if two algebras?
You can add simply connected.
Yeah, and then it's like others,
yeah.
and then you can use that image.
The thing is that you can quotient one connected group by a discrete subgroup and get some and get rid of these good elements. So maybe not in all connected. So that's what I'm worrying about. Okay, so Cartan subalgebras exist. Yeah, let's take some. Yeah, you can take simply connected. They're all there, at least. Yes. And second is that every two Cartan subalgebras are conjugate. Proof, or at least like a sketch of proof, I don't know. So for that I need to introduce regular elements. So let me denote, so for each element in X, in G's, sorry, denote n of X to be the nullity of at X. So nullity means the dimension of generalized eigenspace corresponding to 0. So it's not only kernel of this, but also things that become kernel after subsequent action of at X. Well, I'm not only including, I'm including Jordan blocks together to this, not only like the beginning of a Jordan block. Okay, so that's what I'm doing. So it's multiplicity, I don't know, it's like geometric multiplicity, algebraic multiplicity, it's one of these two. I think it's algebraic. It's a multiplicity of this root in minimal polynomial for the X. Yes.
It's also a sum of dimensions of all characteristics with 0.
Yes. Now, by definition, X is called regular if n of X is minimal possible along all n of Y's. It's greater or equal than 1 for each X, for sure. Right? Because it commutes with itself. Very well. So X is regular. And let us denote the set of all regular elements in G by Greg. Okay. All regular elements. You may ask me if this is related to regular elements that we saw for root systems. So they are they actually the same if you restrict it to H. So intersection of G-rec with H, well, duals of them gives you exactly regular elements in H star. Yeah. All right. So now.
So set of simple roots is dual to the Dirac intersection with Cartan?
A set of simple root. No. G-rec is something dense and open. So it's like it's something that does not belong to these hyperplanes, right? So everything that belongs to Weyl chambers, like interior of like Weyl chambers. So if you consider dual to that, it will be intersection of G-rec with H. All right. So then I have the following lemma. That centralizer, so lemma, C of x, which is all y in G all y in G such that y commutes with x. So for so lemma goes like this. So for every regular semi-simple x, Cx, also we can denote it as like this, Hx, is a Cartan subalgebra. Okay, so this we need, and this is not all that I would like to claim for this lemma. Also, each Cartan subalgebra of G is of the form Hx for some x from G-rec. Okay, so proof of lemma goes in several claims. So first let me claim that, so claim 1 is that C of x is nilpotent. So this is because if I take, maybe I also will denote sometimes this is G0. Nilpotent is Lie algebra. Okay, so let me take add. Right, so let me take just some y in G0 and consider the following line. Well, xt is yx plus ty. Then I claim that add xt. So first of all, G0 is invariant with respect to add xt, right? Because both x and y are in G0. So therefore, we're staying in G0 if I act by this element. So therefore, I can consider its image in the quotient. And I denote it like this. Sorry, it's not restriction, but rather image in the quotient. And I claim that this is invertible for small t. This is because add x image in this quotient is invertible. I kind of killed like I killed kernel and all null space by killing G0. Right? It's all in the centralizer, invertible. Right? So therefore, for small t, I still have invertible situation here. So therefore, still now space of xt is inside G0 for small t.
Essentially, what we're saying is that the set of invertible matrices is open, right?
Yes.
And that's why.
Yeah, I can move it a little bit, still inversible. So therefore, it means that null space of add xt is inside G0. So generalized eigenspace corresponding to 0, it's all in G0. Kernel is of course there, but I mean, so it's generalized eigenspace or corresponding to eigenvalue 0. So it's all like, for example, kernel, and everything that I can, that if I apply add x sufficiently many times, I'll get to the kernel. So in other words, yes, but dimension of this null of add xt is exactly n of xt, right? But x is regular, so therefore it is greater or equal than n of x, but n of x is exactly the dimension of its centralizer. So therefore it is actually equality.
Why nxt is more than n of x?
So centralizer is exactly a generalized so it's actually also semi-simple, right? So generalized eigenspace corresponds to just a kernel, right? So now nullity of x, now subspace of x is a kernel of x because it's semi-simple. But because it's regular, yes, it's semi-simple, it's diagonalizable, no Jordan blocks, right? It's no generalized, like non-trivial generalized eigenvectors. So therefore, it's exactly dimension of kernel of adjoint action of x.
Yeah.
Kernel of adjoint action of x is C of x, centralizer. So therefore, we have this. So therefore, we have equality here. It means that it means what? That add xt restricted to G0 is nilpotent. But xt is x plus yt. X just commutes with anything in G0, right? Because G0 is centralizer of x. So it means that add y restricted to G0 is nilpotent. And then Engel's theorem we have that G0 is nilpotent.
So isn't Cx is centralizer of x
Yes, but I'm using also that X is semi-simple. So kernel actually coincides with generalized kernel, if you wish, with null space. Because you don't have blocks. So it's diagonalizable. In Jordan normal form, you don't have non-trivial blocks. X is semi-simple, yes. For every regular semi-simple X, we, yes. We proved lemma, right? But then I would like, so claim 2 is that actually C of X is abelian. So C of X is abelian. Why? Because of the following. So for proof of this claim, I need, so it's nilpotent, therefore C of X coincides with its radical, right? But then, so it's solvable. So nilpotent, therefore it's solvable, so it coincides with this radical. On the other hand, I would like to say that C of X is also reductive. We already kind of proved something like this. We had like statement that G0 corresponding to like a toral subalgebra is reductive. So the same statement here. So I take killing form, and its restriction to G0 should be non-degenerate. It's the same, it's like a standard argument that on G alpha, tensor G negative alpha should be non-degenerate, right? It still works. So before we had this to be Cartan subalgebra, but we don't need all this additional assumptions on Cartan subalgebra. We just need that, so we just need this for just single element, right? Decomposition into eigenspaces. Right, it's just invariance of Cartan, of a killing form, right? On different G alphas should be 0, so therefore on G alpha tensor G negative alpha it should be non-degenerate because it's non-degenerate on G. Okay, and G alpha is the eigenspace for just single element there, X. Right, so this is non-degenerate, and also it is trace form for C of X with representation with C of X module G. Yes. So you just applied the same argument that we did. Remember, we had a toral subalgebra, and we had decomposition into common eigenspaces, like this. Now, instead of toral subalgebra, just take one element X and consider the same decomposition. It's semi-simple, you still have this decomposition. And consider the same argument that we proved to see that G restriction of killing form on this is non-degenerate. It should be non-degenerate because on diff, if alpha is not equal to negative alpha here, killing form should be 0. Yes.
So this was a task for 7 or what?
No, it was a proof.
That was stated for toral subalgebras. if I restrict to common eigenvalues. But now let me take not at all, okay, this is still total subalgebra, but spanned by one element. Okay, you can say it like this, which is X.
What will be G0 in that case?
G0 is exactly C.
It's exactly everything that can use with X.
It's,
But like, what exactly, how was our statement like looking that we say that we take X,
mhm.
total subalgebra, or expanded X, right? Is it total subalgebra?
Yes.
How do we actually get that it's non-degenerate on G0 exactly? Like,
Well, you just take alpha to be 0, so it's G0 tensor G0. So it's so its restriction of killing form to that should be non-degenerate. So therefore, its restriction to G0 is non-degenerate. Yes. So therefore, it is reductive. So I found some trace form which is non-degenerate. So therefore, by some criterion, it is reductive. Therefore, radical coincides with center. Right? But so therefore, C of X is its own center. So therefore, C of X is abelian. So claim 2 is proved. So the only thing that is needed now to for the first sentence here. So Hx, we're proving that Hx is a Cartan subalgebra. We just need to prove that every element is semi-simple. Right? Okay, time check. I think I'm over time already. So let us prove at least the existence. So maybe we will not finish all this ambitious stuff. So what I'm saying is that, okay, I would like to see that every y in C of X is semi-simple. So let me take Jordan decomposition. And then let me take, so I would like to say that ys, so y commutes with x, right? Because y is in the centralizer. So therefore, y commutes with xs as well. So that's the statement, one of the statements in Jordan decomposition that we have.
what is XS?
Is sorry, x
S should be
should be here. What I'm saying is that ys is also in C of x, right? And also yn is then also in C of x. But then I take add yn, it is nilpotent. I take add x. This one belongs to, so x belongs to C of x, and C of x is commutative. So therefore, these two things commute. So this is because C of x is commutative.
So why
this is one of the statements in Jordan decomposition. So if I have some element such that it commutes with y that we decompose, then it commutes with semi-simple part. So I'll just refer to this.
It was the last part of the statement.
Yes, yes. But this is because C of x is commutative, and yn is inside C of x, and x is inside C of x. But then add yn is nilpotent, right? Therefore, the product, since they commute, is also nilpotent. But then a killing form of yn with x is 0. So killing form is trace of this, and this is nilpotent. Right, so trace of this is exactly k of y and x. Because I take some power of it, and this power goes to here since they commute. Yes. Very well, but k restricted to C of x is non-degenerate. Right? So therefore, this means that yn is 0. So therefore, y equals ys is semi-simple. So we proved if I take x semi-simple regular element, then C of x is a Cartan subalgebra.
So like k is non-degenerate, but isn't non-degenerate mean that there exists some element for yn that it's not 0 with him?
Yes. Right. This is for any. I'm sorry. This is for any z. For any z from C of x.
That's why.
Yes. You're right. This should be done like this. Otherwise, this implication is not correct. But still, if z is a C of x, the commutativity gives me this. All right. So, but then what? Okay. So we proved that C of x is a Cartan subalgebra. Okay. This one requires something, and we over time, so maybe not prove this thing. But for existence, we proved enough. So let me take some regular element. So regular elements I do have, because G regular is an open dense subset. Actually, it's like complement of some algebraic set. Yes.
But minimal is algebraic.
No, it's a complement of algebraic. You consider so this is a generic, right? Not minimal means that some right. Okay. So in more details, if you consider add x, right, and determinant of like characteristic polynomial, right, then you have it is sum of some coefficients, right, I from 1 to whatever dimension g. And let me take this minimum y and g to be some number r. Yes, so this the fact that that nullity is r, I think it's something like AR is not equals to 0.
Well, that's characteristic polynomial, not minimal.
Yes. So actually you need, do you need characteristic, but minimal, yeah, I think you need characteristic polynomial for nullity.
The matrix to the power of n. When you have minimal, you have only
the biggest block. Minimal, you're only counting the biggest block.
Yeah.
In characteristic, you really count the multiplicity, like you sum them out.
But is it true that if minimal polynomial of degree of r, then AR is not equal to 0? Why is it so?
So what I'm saying is that, okay, so that it means, so AR
that minimal of n of y equals to r, that this polynomial for all this polynomial is divisible by t to the power of r.
Also, I think it's n minus I should be here. So it means that well, because you start, so you start, so you will have AR T n minus R, right? Maybe the other way, yes.
Because if you have the dimension of
yes.
equals to r, then the first polynomial is divided.
I would like this to be TR times some polynomial. And this polynomial should have should not be 0. So yeah, this is the condition. I would like this to be like that, where this polynomial has no root 0.
Yeah, right.
So this is a generic condition.
Yeah.
You agree? Okay. And then, so where are we? Yes. So existence. So let me take y, just some regular element, and consider its decomposition. Then I claim that ys is also regular. So this is Jordan decomposition.
So what do you want to prove? Existence of regular elements?
Semi-simple regular element.
Yeah.
So ys is regular and semi-simple, of course. So therefore we proved, so corollary, so we proved part 1 of the theorem. Part 1 of theorem is proved.
Yeah, and ys is regular. What we take it from?
Well, because it has the same diagonal in Jordan form as y has, and multiplicity of 0 here is exactly how much zeros in this diagonal.
There you just don't have blocks. Yeah.
Yeah.
Because
That's why it's important to have nullity, not the dimension of kernel here. Well, because in Jordan block, then I would just count only zero that starts my Jordan block, not these zeros.
It will be, if we take without nullity, we just take all regular semi-simple.
Yeah, I just count number of blocks corresponding to, if I just compute dimension of kernel, I count,
It will be less.
yes, so here, this will be less.
Yeah.
And then I cannot claim that this actually is regular. Yeah.
Well, but the nullity for YS is the same for the dimension.
Yes, for YS it's true.
And why we need this about algebraic
Чтобы вообще были какие-то регулярные элементы.
Либо открытое множество всегда есть. Кроме если оно не пустое. Хотя мы не проверяем, что оно не пустое. Нет, ну это не сказали, что это пробовалось.
Да, я вообще никак не пользуюсь тем, что это C-фикс. Это правда вообще любого абелевой вещи. Ну вот именно это рассуждение. Что
Да любой сейчас пользовались ли мы здесь чем-то?
То, что любой элемент абелевой подал.
Не, ну я извиняюсь, мы пользовались тем, что YS тоже и YN тоже все от X. Нет, ну допустим у нас абелева, да, действительно. Допустим абелева, да, это правда.
То есть для любой абелевой, любая абелева подал состоит из полупростых только.
Это, кстати, сейчас. А мы еще пользовались, что форма киллинга
Вот, то, что форма киллинга.
не вырождена. Вот это, да. Не, ну в том смысле, что она уж точно вырождена, если я возьму просто форму киллинга на абелевой. Но она вырождена. Вот. А здесь мне вот...